Good morning, all. We can start it for today. I'm about to start for like 10 minutes earlier because uh, I have some deadline work to be submitted today. So sorry for that. So we'll be starting 10 minutes earlier today. Okay. So it's almost like 2:55, 2:53, and 2:55. Just 5 minutes starting early. So I welcome you all. A very good afternoon to one and all. So we are here on the last live interactive session of chemical engineering thermodynamics. Okay, so this is the last live interactive session we are going to have for this course, and I think hopefully after like 1 or 2 weeks there will be the final examinations for the same. So what I've been saying is that we'll go through some of the week-like contents, and please let me know if you have any issues or problems related to some of the content that we have been having through the week 1 to week 12. Okay, so we'll go through the week 12 content and we'll solve some of the numericals and the assignment tutorial problems later to that. Okay, so very good afternoon to one and all. So this is week 12 live interactive session on chemical engineering thermodynamics, a course open on NPTEL online certification portal. So this is the course that is opened by Professor Gargi Das. She is a professor in the Department of Chemical Engineering at IIT Kharagpur. And just a little bit about myself. So I was the teaching assistant, and this will be the last live intersection for me as a teaching assistant for this course. I am Raspi Shubham Ajikumar, and I'm a PML scholar in the Department of Chemical Engineering at IIT Madras. Okay, so like I said, this is a week 12, and we are going to have like last live interaction today for the week 12. So the week 12 content on the portal was somewhat like this. So the content was, if you have seen the sorry, if you've seen the vector content, the first one relates the chemical reaction equilibrium, that is CRE, somewhat concepts related to the chemical reaction equilibrium, and the second is equilibrium constant and its estimation. And more contents in the week 12 are based on the equilibrium, that is the reaction equilibria and the equilibrium constant and its estimation, reaction relation of the equilibrium constant to its composition and its various operating conditions. Okay, and similarly we have a relation of equilibrium constant to the composition uh, repeated, and the miscellaneous concepts in the later. So this is what how the vector lines that is related to the equilibrium in the reaction and this concept of operating conditions on the equilibrium conversion. Okay, so what we'll do, we'll start with some of the basic questions, and then we'll go on to solve some of the numericals directly related to the vehicle content. So if you see the question 1, so 6 kg of air, assume idle, is heated from 40 degrees Celsius and 1 bar at pressure until its temperature reaches 250 degrees Celsius. Assuming the process to be isochloric, that is a constant volume, calculate the change in the internal energy, delta U, and enthalpy, as well as heat and work interactions during the process. So considering only the PE type of work. So we have given the molecular weight of air, that is 29, and specific heat at constant volume, and the universal gas constant R. So we'll just start writing 6 kg of air assumed to be ideal gas. Okay, temperature is 40 degrees Celsius, pressure is until temperature reaches T final is 250 degrees Celsius. Okay, now so what we'll do, T1 is equal to this, and this corresponds to T2. Okay, so now what we have is like different conditions. So what we'll do is that we'll convert first into degree Celsius, Kelvin. So this comes out to be 313 Kelvin and 523. Okay, now pressure is given as 1 bar. So 1 bar is 1 into 10 is to 5 Pascal. So 1 bar is 10 is to 5 Pascal. Specific constant volume is given to us as 20.78 joule per mole into Kelvin, and universal gas constant R is 8.314 joule per mole Kelvin. Okay, so from this what we'll find out is the number of moles, N. Number of moles of air, N is equal to, so it is number of moles is given weight by molecular weight. So given weight is 6 kg is 6000 gram, molecular weight is 29 gram per mole. So grams cancelled out and it turns out to be 206.89 moles of air. Okay, so this is the first. Now we need to find out, now since the ideal gas is given, so ideal gas is PV equal to, ideal gas equation is given by this. Therefore, if you take V1, ideal gas component 1, so V1 equal to NR T1 by P1 is equal to 206.89 into 8.31451 into T1 temperature in Kelvin divided by P1 is 10⁵ Pascal. That it comes out to be 5.36 meter cube. So this is P1. Now since this is an isochoric process, so isochoric means constant volume. So this assumes V1 equal to V2 equal to, so V2 will also be 5.36 meter cube. Okay, now first we need to find out the change in it. Now we know that del U is equal to NCV delta D, that is T2 minus T1, so 206.89. CV value is 20.78 into T2 is 523 minus 313. This comes out to be 902.83. Okay, now second we have to find out the work done in terms of PV, right? So W is equal to PdV V1 to V2. So this, since the volume is constant, that is an isochoric process, so it implies work done equal to 0. Third is in Q, that is heat. So Q is equal to U plus W, so Q is equal to delta U plus W. So 902.83 plus 0 comes out to be 902.83 kilojoule. Okay, and similarly you can find out the fourth one, that is enthalpy, H equal to U plus P vector del U plus P del V. Okay, so this is how we can solve this equation easily. So what I've been doing is that in the week 12, since I've seen like different reactions and the equilibrium concepts, so what I'm doing is that I'm just revising it from the week 1, then I will go to the week 12 contents as of now. Okay, so this is how we have found out del U, del H, Q and W. Okay, so this is 4 things that has been asked in the question. We'll move on to the next question. So if 1 mole of an ideal gas at 298 Kelvin, that is at room temperature, undergoes a reversible isothermal process where the molar volume of the gas changes from V1 to V2, what is the entropy change associated with the process? Okay, so this is also like related to the week 1 and week 2 content. Now since we know that the entropy change, that ds equal to dq by t or del s equal to del q by t, which implies ds equal to dq by t and q is equal to u plus p dv by t. So this is the first equation. Now for an ideal gas, is a function of temperature. Internal energy is a function of temperature only. And for an isothermal, du equal to 0 since temperature is constant. Therefore, for given question of 1 mole of an ideal gas, that is ds equal to du is 0, so this will be 0, right? This sum will be 0. is equal to P dV by T. Therefore, del S R ln V2 by V1. Now we will replace this equation with PV equal to nRT, that is an ideal gas equation, and we can summarize into this. Now given R value, that is 8.31451 ln of V2 by V1, that is 0.041 divided by 0.023. Therefore the change in entropy comes out to be 4.6 joules per Kelvin. So this is how the simplest answer you can arrive. We are just revising from the weak form the basic concepts. Okay. This is like how the change in internal entropy can be calculated from the fundamental concepts of enthalpy and isothermal of the given to the isothermal processes. I will go to next question. So a tank of 5 meter cube volume is filled with 10 kg ammonia at 500 Kelvin. Determine the pressure exerted by the ammonia using the ideal gas law, assuming ammonia observes the van der Waals equation of state. Okay, so this is related to the non-ideal equation of states of gases. So volume is 5 meter cube and mass is given to us as 10 kg. Temperature is 500 Kelvin. Since ammonia is an NH3, so ammonia's weight is 17 to 10 kg per mole. So I'm taking in mole. If I write kg per kilomole, it's 17. Okay. Now we know that for an ideal gas, PV equal to nRT for an ideal gas. Okay. For the van der Waals equation, P is equal to RT upon V minus V minus A by V square. So this is van der Waals equation of state. Okay. Now we know that the number of moles given weight is 10 kg. Molecular weight is 17 into 10 to minus 3 kg per mole. So this will cancel out. It turns out to be 588.23 moles. Okay. Now we know that the volume can be molar volume is 5 meter cube upon the number of moles 588.23 moles is 8.5 into 10 to minus 3 meter cube per mole. So this is the molar volume. Now I have been given two cases. First case is for an ideal gas. Okay. So we will write Pv equal to nRT, that is P equal to N upon V RT. So this is nothing but the 1 upon molar volume into RT. Therefore pressure is R is 8.31451. Temperature is 500 Kelvin. Divided by molar volume we just found it out is 8.5 into 10 is to minus 3. So pressure turns out to be 0.489 megapascal. Okay. Now second case is for a van der Waals equation of state. You have to find out the pressure using van der Waals equation of state. Okay. So we know that P equal to RT upon V minus P minus A by V square. So R is 8.31451, temperature is 500, molar volume is 8.5 to 10 to minus 3, and V value is given to us as 0.037. So I will take 10 to minus 3 common. A is given as 422.546 into 10 is to minus 3 divided by molar volume, that is 8.5 into 10 is to minus 3 whole square. So if you solve this entire equation, you find out the value of P in terms of megapascal. From the Handel equation of state, that turns out to be 0.485. Okay. So you can clearly see the change in the values of pressure from Mendel equation of state and ideal gas equation of state, and this might be due to the uh, assumptions that made that during the solving of the Mendel, no, that is a non-ideal gas equation of state. Okay. So we'll quickly move on to the next question. I hope this might be revising some of the concepts from starting from the week 1. So it's like we're going to starting from the basic questions and we are moving up to the week 12. So because this is live interactive sessions, I wanted you to remember some of the concepts quickly in just 1 or 2 hours interactive session. Okay. So the next question is, a refrigerator of molecular weight 45 kg per mole exhibits a saturation pressure of 50.74 kilopascal and a latent heat of evaporation of 220.56 kilojoule per kg at 50 degrees Celsius. Okay. Estimate the saturation vapor pressure of the refrigerant at minus 10 degrees Celsius. Okay. So we'll write down the molecular weight first. That is given to us as 45 kg per mole. Saturation pressure of 1 is given as 50.74 kilopascal. Latent heat of vaporization 220.56 kilojoule per kg. Temperature 1 is given as 50 degrees Celsius plus 273 is equal to 323 Kelvin, and T2 is equal to minus 10 degrees Celsius plus 273 is equal to 263 Kelvin. And we have to find out the vapor pressure of second component. Now we have, like, we can find out first the number of moles. So the weight divided by molecular weight. Therefore, 220.56 kilojoule per. Since we have been given the latent heat of vaporization, we will write mole per kg. So this kg can see is cancel out, and the number of mole. So this, from this you will get kilojoule per mole. Now we'll use this value later, that is the enthalpy of vaporization value in terms of moles. So we have this equation ln of P2 set on ln of P1 set is equal to latent heat of vaporization by R 1 upon T1 minus 1 upon T2. So if you use 1 upon T2 minus 1 upon T1, so the more common thing will be that the minus sign will come out, that is minus delta H of vaporization by R 1 upon T2 minus 1 upon T1. Okay. Therefore, ln of P2S divided by P1 is 50.74. Latent evaporation in kilojoule per mole is 992.925. Okay, this is done. So this is latent rate of vaporization in kilojoule per mole. 992. R is universal gas constant 8.31451 kilojoule per mole Kelvin. And T1 minus T2. So you can find out the value of P2 saturation from here. So what we'll do, we'll take the exponential of this, that is minus 0.8, that it corresponds P2 saturation as 21.83 kilopascal. So this is the answer. Okay. So I will quickly move to the next question. So the question asks related to the what is the fugacity coefficient of a gas obeying the equation of state PV equal to RT 1 minus is at 1 bar. The pressure P is in the equation is in bar. Assume constant temperature conditions where fugacity is given as this. So this is like from the week 6th or 7th, I think so, related to the fugacity and fugacity coefficients, and similarly activity we have discussed during the week 6 and week 7. So start writing. So we have been given an equation of state that is P equal to S PV equal to RT 1 minus 0.00513 P, and pressure is given as 1 bar. Therefore RT D ln of F is equal to VdP. So this is first equation and this is second equation. Both are given to us here. If you see in the question, now we have from equation 1, if you rewrite whatever V equal to RT minus 0.0513 into 1, that is the pressure. Okay, therefore I will try to rearrange ln of F by dP is equal to RT ln upon P minus 0.00513. So this RT will cancel out, and D ln of F is equal to ln upon P minus 0.00513 into dP. So this is the equation of 3. Now, okay, so don't have space. So what I will do is that I will just write it here. So it turns out if we take the ln on both the sides, so what will ln of F by P is equal to 0.00513, and ln of F by P is nothing and the fugacity coefficient is equal to 0.00513. So phi is equal to exponential of 0.00513, it comes out to be 0.995. So this is the answer. Okay, you have just rearranged and taken the ln values, because d ln of F by d ln of P will comes out to be this. Okay, now we'll move to the next question. So the vapor pressure of benzene and ethyl benzene. So we have given two components. Component one is benzene and second is ethyl benzene. We have to use the Antony constants. This is first equation, means the Antony equation 1 and Antony equation 2. But T is in degree Celsius and P is in Pascal. Okay. Assume that they form an RL solution. Calculate x1 and y1 at 25 degrees Celsius and 10 kilopascal. Okay. So what we'll do, we have been given temperature, so we'll find out the vapor pressure of component 1, that is 13.8594 minus 27738.78. Temperature is 25 plus 220.07, and ln of P2 is equal to 14.0045 minus 3279.47 divided by 25 plus 213.20. Now in x1, now we don't know x1 and y1. Okay, and temperature is given 25 degrees Celsius, and total pressure is 10 kilopascal. So putting this value, so we will find out P1 set is equal to 12.693 kilopascal. So this is the P1 and the P2. and these values we have found out from this one. Okay, now we know that total pressure Pt is equal to x1 P1 set plus x2 P2 set, therefore x equal to P minus P2 set upon P1 set upon P2 set. Okay, so we have like total pressure is 10 kilopascal minus 1.267, P1 is 12.693 minus 1.267. So therefore x1 turns out to be 0.764. Now we know that yi into p from Raoult's law is equal to xi into Pi saturation. So component 1 you can write y1 into pt is equal to x1 into p1 saturation. Therefore y1 is equal to x1 p1 on where total pressure is 10, it turns out to be. So this is the answer. Okay, so this is how we find out the mole fraction of paper and the liquid phase using the Raoult's law and the total pressure conditions. That is how this vapor pressure can be related to the total pressure. Okay. This is from the recent weeks like non-ideal equation for the activity coefficient models, which are known as the like Margol's 2 suffix, Margol's 3 suffix, Van Laar, NRTL, that is non-ideal two liquid equations, and like various equations we have been solved for the non-ideal activity coefficient models. So this relates the Van Laar thing. So we'll go to the equation. So it relates the Van Laar constants A and B for the system of nitromethane and carbon tetrachloride. So we given component 1 and component 2 at 45 degrees Celsius. Okay. 2.23 and 1.96. Okay. Respectively, calculate the activity coefficients, that is gamma 1 and gamma 2 for component 1, that is nitromethane, and component 2, that is carbon tetrachloride, in a solution containing 60 mole % of carbon tetrachloride. Okay, we will write A is 2.23, B is 1.96. We need to find out x1. x2 is given as 60 mole %, that is 0.6, and we know that x1 plus x2 equal to 1. It corresponds to x1 is 0.4. Now using the Van Laar constants, we know ln gamma 1 equal to A upon 1 plus ax1 upon bx2 whole square. A is 2.23 upon 1 plus 2.23, b is 1.96, x1 is 0.4, 0.6 whole square. So to solve this, we'll find out 2.057 as gamma 1. That is, what we'll do is that whatever the value that will come, we will take the exponential of that is here issued there, and simplifies gamma 1 is equal to 2.057. Similarly, ln of gamma 2 is equal to b upon 1 plus bx2 upon ax1 whole square. So b is 1.96, 1 plus 1.96 into 0.6 divided by 2.23 into 0.4 whole square. So this implies gamma 2 equal to 1.44. So this is the answer, that is activity coefficients gamma 1 and gamma 2. Okay. You solved the question using this many times in the week 6, week 7 using this non-active models for uh, uh, the active models using the non-ideal equation of states. Okay, so this is one of them, that is the NR equation of state for the active models. So we have like gamma 1 equal to 2.057 and gamma 2 comes out to be 1.44. So these two are the final answers. So now we'll move to some of the week's later content. So cyclohexane and benzene, two components have been given to us, which forms a real solution at temperature of 313 Kelvin. So we'll write out cyclohexane component 1, benzene at component 2, temperature is given as 313 Kelvin. Okay. The vapor pressure of the components at this pressure is, so the vapor pressure is given to us as 24.62 kilopascal and P2S is 24.41 kilopascal respectively. Now we have been given Ln gamma 1, that is activity, liquid phase activity coefficient is given as 0.458 x2 square. Ln gamma 2 is equal to 0.458 x1 square. What is the total pressure exerted by the equivalent solution of the above components in kilopascal? So since we have been given an equivalent solution, so it means x1 equal to x2 equal to 0.5. Therefore, Ln gamma 1 equal to 0.5458 into 0.5 is equal to 0.1145. And similarly, Ln gamma 2 will be the same, that is 0.1145. Okay. Now what we will do is equal to gamma 1 equal to gamma 2 is equal to exponential of 0.1145 comes out to 1.13. Now we know that we have been asked for a total pressure. Okay, so total pressure will be PT, and we have been given the vapor pressure of the component 1 and component 2. So x1 plus x2, and here we have an activity coefficient model, so it will be gamma 1, gamma 2. Now we can like rearrange this equation, since we know that the kilo components are there x1 and x2, so we can write as PT is equal to gamma 1 x1 P1 set plus P2 set. Therefore, PT is equal to gamma is 1.1213, x1 is 0.5 because an equivalent mixture, and 24.62, that is vapor pressure of component 1, and vapor pressure component 2 is 24.41. This turns out total pressure to be 27 kilopascal. So this is the final answer. Okay, since we know that gamma 1 equal to gamma 2 and x1 equal to x2 because this is an equivalent mixture that is given to us already. Okay, so I have just simplified the equation and arrived to a final answer. So this is what they are asked to find out the total pressure, that is PT. Okay, so we calculated that. Now we'll move on to some of the other questions related to the weight 12 actually, and these are already been there in the assignments, but I'll just try to quickly solve it out for you guys for like some 2 to 3 more numericals. So estimate the degree of freedom. So these are much more related to the equilibrium in the reaction system, like the chemical reaction equilibria and the equilibrium constants in the reaction equilibria, how they can be related, all the things. So estimate the degree of freedom of a reacting system. Reaction is given below where the number of independent reaction is 1. So N2 plus 3S2 is equal to 2NC, that is the ammonia synthesis reaction, the Haber's process. So degree of freedom is given by F equal to C minus plus 2, where C is the number of components, number of phases, and this R will also mention. I have not given it to you earlier, but in reaction equilibria, the R will come because it tends to the reaction. So it corresponds to the number of independent reaction. Okay, so the number of components given to us is 3, N2H2 and S3. Number of phases, you can see the number of phases is 1, that is on a gas phase only, and R is the number of independent reaction is 1, that is given to us. So we'll write F equal to component is 3 minus 1 plus 2 minus 1, so it comes out to be 3 is the answer. So degree of freedom for this system is 3. Okay, just remember this R will be taken into consideration for reaction. If the reaction is not given to us and just normal like liquid and vapor phase are in equilibrium or something is given to us, you can include directly F equal to C minus P plus 2. But this here we are including the reactions also. Okay, so that's why you have to include R, that is the number of independent reaction, it will be negative. So F equal to C minus P plus 2 minus R. Okay. Move to next one. So find the equilibrium constant at 100 Kelvin. Given the equilibrium constant T1 at 7 to 10 to minus 5. Standard heat of reaction may be assumed to be constant and equal to 45 kJ in the temperature range of T1 to T2. Okay, you have to find out the equilibrium constant K. So that's the equilibrium constant. We have been given two different temperatures, K1 and K2, be the equilibrium constant at T1 of 298 Kelvin and T2 of 800 Kelvin. Okay. Now from Van 't Hoff equation, we have ln of Ka by dt at constant pressure is equal to minus delta H naught by RT square. Now on integrating above equation, that is this one, we'll get ln of K2 K1 is equal to, I will take the negative sign inside, so it will be 1 upon T1 minus 1 upon T2. Okay, now we have given delta H as 45 kilojoule. Standard heat of reaction may be assumed to be constant equal to 45. So delta H naught is equal to 45 into 10 to 3 joule. K1 is equal to 7 into 10 to minus 5. T1 is equal to 298. T2 is equal to 300 Kelvin. Substituting, you will get the value of K2. So we are in the equation K2 equal to 7 into 10 to minus 5 into exponential of 45 into 10 to 3 divided by 8.31451, 1 upon T1 minus 1 upon T2. On solving this, we'll get the constant 2 as 6.235. Okay, so this is the answer. Okay, we move to next one. So this is like the for the reaction equilibrium. So calculate the extent of reaction for the following ideal gas phase reaction, as a system pressure of 42.85 bar and a temperature of 500 Kelvin. Initially, 1 mole of ethane and water is present in the field. So methane, sorry, ethane and water reaction gives to form of ethanol. The equilibrium constant Ka at 500 Kelvin is given to us this. So we need to find out the extent of reaction. Okay. So from above stoichiometric, so difference in the stoichiometry. If you take this equation, ethane plus water gives ethanol. So difference in stoichiometry, it comes out to be reactant minus product 2 minus 1. Okay. So now what you have to do is that you will find out the component first. Write out the number of moles in feed, moles at exit, that moles at feed, moles at exit. Get it clearly. Exit. Okay. So now we have three different components: C2H4, H2O, and C2H5OH. Okay. Now we have the moles in feed is 1, 1, and this is the reactant, that is 0. Moles at exit will be 1 minus epsilon E, 1 minus epsilon E, and this will be epsilon E. Mole fraction at the exit will be summation of all this is 2 minus epsilon E. So it will be mole fraction is given mole divided by total mole fraction. So 1 minus epsilon E divided by 2 minus epsilon E. Similarly for here, 1 minus epsilon E divided by 2 minus epsilon E, and this will be epsilon E divided by 2 minus epsilon E. That is a mole fraction at the exit. Okay. Now what we'll do, let phi be the mole fraction. You can write any component like x as that. Therefore Ay is equal to mole fraction of the component form EH y y of C2H4 into y of H2. Okay, because these two are the reactants and the ethanol is product. So it epsilon E divided by 2 minus epsilon E whole divided by 1 minus epsilon E divided by 2 minus epsilon E whole square, because they both are same. Okay, so this corresponds to epsilon E divided by 2 minus epsilon E divided by 1 minus epsilon E whole square. Okay, so this 2 minus epsilon will be cutted out, and there will be only one 2 minus epsilon E. Now we know that Ka is equal to K phi into Ky into Pv. For an ideal gas, phi equal to K equal to 1 into Ky into Pv is equal to 1 into Ky into 42.85. Stoichiometric coefficient is -1. Therefore 42.85 into Ka is equal to Ky. So what I'll do is that directly replace Ky value this to here, because this is Ky. Okay, on solving this we will find out the value of epsilon E, that comes out to be 0.52. So directly substitute that value there, and you can use the scientific calculators for finding out this value. Okay, so this is one set of question. This is another one. So estimate the equilibrium mole fraction of ethylene this is the simplest one, like the similar to the previous question, but how can you find out? Estimate the equilibrium mole fraction of ethylene and ethyl alcohol in a mixture after reaction. See question C. So this is the previous question. And this one I have taken from the assignment problems of the week 12 itself, just to cover up some of the questions for the reaction equilibrium. Okay, so what we'll do is that mole fraction of phi of C2 H4 1 minus epsilon e nearby 2 minus epsilon e. Now epsilon e value is 0.52 divided by 2 minus 0.52. Distance away 0.324, and similarly y of C2 H5 epsilon e upon 2 minus epsilon e. So this is nothing but the mole fraction at the exit. So 0.52 upon 2 minus 0.52 is 0.35. So the correct answer is A. So this is related to the previous question. What we have done, we have taken the value of the epsilon e, that is the equilibrium constant, and then we have to use this value to find out the mole fraction of the components, that is of ethylene, ethyl alcohol. Okay. The last one for today. So consider the reaction, that is calcium carbonate gives calcium oxide plus carbon dioxide. Estimate the equilibrium constant of the reaction at 500 Kelvin. Given the standard gives free energy at 500 Kelvin as minus 9.8067 kilojoule. So what we'll do is that, so the reaction is given as CaCO3 solid gives calcium oxide solid plus CO2 gas, and we have been given delta G at 500 is equal to minus 9.8067 kilojoule. Now since we know that delta G is equal to minus RT ln of K, and K is the constant, therefore minus 9.8067, that is in kilojoule, will convert into joule, is equal to minus 8.314 into T is 500 ln of Ka. Therefore Ka, what we'll do, we'll find out the value of first ln Ka, then we'll put ln A on the RHS side, it will be exponential. So Ka exponential of the value what we have been trying to solve that equation. So Ka turns out to be finally as 20.58. So this is the final answer. So this is the equilibrium constant, how you can identify, because delta G is equal to minus RT ln K. Okay, so I think we have covered almost all the things for, I'm trying to put it up for today. I think ends here. So today we have covered up all the like small questions from week 1 to week 12, and we have solved some of the numericals from the week 12 assignment problems also. So this is what I have for all this live and tech session for today. So I'm wishing all the students who are going to appear for the final examination of chemical engineering thermodynamic IITKGP course, so which is going to be happen in like coming week, coming up weeks of like week 1 or week 2 recently. So all the best to all the students. Please go through all the lecture contents once before appearing for the examination. Please start brush up all the topics and try to solve as much as numericals as you can. Please go all the live interactive sessions which has been uploaded into the YouTube, as well as the PPTs has been uploaded in the PDF form in the NPTEL SWAM portal. I will suggest all the students, please, it's not suggesting, I will request all the students please go through to all the live interactive sessions. And still, if you have any issues or any problems, please do let me know before the examinations, so we can have one more live interactive session which just solve out all the problem doubts for all of you guys. So wishing all the best for all the students for the final examination of our chemical engineering thermodynamic course. Uh, thank you for having with me, and I enjoyed a lot from this week 12. I was the TA. I learned a lot I brush up my basics. So it was like 2 to 4 years ago. I've been learning chemical and thermodynamics. It's very good to have interact with you live interactive sessions. So I think to all the students who have joined these live interactive sessions for the week 12 weeks straight in a row, I also thank NPTEL and SWAYAM portal for giving this opportunity for completing my PMR TA duties as a part of the PMR tenure. So thank you all. Thank you for joining this session. Signing off, Shubham, and all the best to our students for the final examinations. Thank you. Wishing you all the best for your future endeavors. Thank you, guys. Bye bye.